Just start recording.
Yeah. All right. Can people hear me in the back? Okay. Too loud?
Okay, well, thank you everybody for coming. So today we have a special seminar by Huey-Wen, who's from physics and astronomy, but we are exploring a joint appointment here at EPRIC, so we're very excited for her to talk about her work. So Huey-Wen got her PhD from Columbia University in 2006. She then became a postdoctoral fellow at Jefferson Lab, a research assistant professor at the University of Washington, a visiting assistant professor at UC Berkeley, then became assistant professor at Michigan State in 2016, became associate professor in 2021. She became a APS fellow in 2022 for pioneering lattice-QCD calculations of the Bjorkane X dependence of quark and gluon distributions in the nucleon and pion, which have led to rapid developments in the field and outstanding contributions to cross-community efforts to combine lattice inputs with experimental data to advance QCD. But she has done a lot of different things, including she's won the MSU Excellence in Diversity and Equity and Inclusion Awards in 2023. She won an NSF Career Award in 2017, a Cockrell Scholar Award in 2020. She's won a Blewett Fellowship from the American Physical Society. She runs a podcast with Brian Stanley on my journey as a physicist. She's made games like this, which are very cool. So without further ado, let's welcome Huey-Wen.
Thank you, Dean, for a very extensive introduction. Okay, so my topic today is going to be something that I have been doing for a while, probably the heart of the matter with a supercomputer. No. Okay. All right. Okay, right. So just a little bit about myself, you know, what you were getting yourself into. I'm coming from a small town in Taiwan. So this is, oops, right. So this is where it is. It's just a little island right outside China. So I'm actually grew up in the very in an area that's really isolated from a lot of major city and unlike some of you, I didn't know I want to do physics until I'm undergrad. So, and then, so I was lucky I was able to, many people in my life, including public education, had guided me to where I am. I can imagine in the parallel universe, if there are millions out there, I'm probably the only one making it to the physics career. There were just so many things had to line up, right, for me to get here. So my preferred pronoun she, her. I have been in didn't say I was in New York. I had traveled around the US, and then I was very lucky that I got the position here, which I have been enjoying a lot since I got here. And actually, I have been telling people that my biggest worry when I first joined here is the winter storm, because I have not dealt with that for a long time. I was in Berkeley, you know, so there's nothing there. When I was in New York, you never had to shovel your own snow. So I'm really thankful to my husband who is doing all the hard work for me. And like many women in physics, I married a physics PhD, and can tell from the crazy Einstein inspired hairstyle over there. And then I have 2 children. We have been seeing some of you before COVID. I guess none of the students are old enough to know that we used to have distinguished lecture. We invite Nobel Prize winner to give a talk like once a year or something like that. And then I would be the embarrassing mom that taking pictures with their kids and things like that, right? And so I was, because of, you know, some of my own situation, I've been looking into starting some events with lattice in woman in lattice-QCD, because we are sort of a computational overlapping with theoretical physics. We kind of have this conversion of very few women on top of very few women subfields. And so for a long time, you know, I was really like to meet other people in our field, and that give me some chances to do so and do feel good. And then I come to MSU. I was lucky enough to get some of the people involved in the APS idea. So for those who don't know, this is an APS effort, try to not just have a lot of DI activity within physics within its own department, right? But we're facing very similar problems. And so this is provide us a platform that everybody can compare notes, share experience. And we also have a lot of people whose research is on the DI direction. And so they can share useful study resources, so you don't have to really doing the effort for one. And so during this process, I think Renko is not here, but Renko was pretty active at the time. And I also got to know a lot of activity that's happening in EFRI that I didn't know about. We actually steal a number of activity and ideas from EFRI's DI effort. So that's something also kind of draw me into the interest of joining this community as well. Right. And so I'm going to talk to you a little bit more about my research, which focus on quantum chromodynamics, QCD. And so basically, if they are undergrad or first, second year students, basically I use high performance computer to study the property of the quarks and gluon, right? Like in the hadron, like most commonly nucleon that you can also compare experiment, or sometimes we study the particle that's coming out in the experimental process, such as pion, who does not sit naturally there with decay. So you have to study them in the collision process. And so this goes to a little bit of advertisement on the podcast, because I myself have gone through a very non-unique path, right? And I was wondering how many people are actually going through that without realizing that. I did not realize that there are other female physicists who took a career break and then make it into group leader in some national laboratory that had never been talked about. So myself was quite interested in those situations. So I sort of start a podcast about that. And if you want to find out more detail, there's a QR code. And we were doing a couple of seasons. And this is really an effort that's mostly led by students. I'm sort of just a contact person to help organize the meeting and reach out to some physicists so that they will respond to emails. And so we have a season on the long range plan that is happening. A lot of you are probably very familiar with this. And we have a few people who are involved from the town hall organization, a little bit of process that I wish I would know when I was a student, because I was never been involved or told about activity like this. And then also talk about their journey, how they get to where they are, a little bit about their research. You kind of see diverse research background that people done, and they're very non-unique path, right? Now, a lot of actually turned out there are a lot more physicists originally set out to do something else. I think in this season, the most different ones is somebody who was originally going to major our science, actually, then later got kind of sidetracked to do astronomy and then nuclear physics. So, yes, so back to the topic on the matter. So what can you do as a student? You actually have been trying to study the structure, right? Since you were a baby, we all smashing things. To label my colleague in the high energy group and the BPS building. So as you grow older, you do smash things with style. So you build very, very expensive machine, gather thousands of friends, and we do the smashing. And then somebody take home Nobel Prize for your smashing. And now we try to build another machine to do smashing. But now this time we are trying to aim for different things. So one of the big projects in US try to study QCD. They try to build an electron ion collider, right? So we are trying to do precision smashing, right? So hopefully this will lead to some Nobel Prize in the some of the future. Right. So I want to do this as well, but I'm not really as skillful as an experimentalist. I try and I realized that's not the path for me. So I took a different path, and I actually quite scared of computing when I was a grad student too. I tried all the other subfields, talked to all the professors and tried to avoid doing computing because I was under this wrong impression that what computing is basically. And because I don't have computing in my undergrad. So for me, it's like there's this giant barrier that I don't know what it is. So I had a lot of weird imagination of what computing is when I was undergrad. And then later I realized that actually, computing isn't so scary. I mean, there are certain computing components you have to be very specialized and even learn how to write machine language for some application, but that's not what I need to do as a physicist. So that's how, and that's what I do. I took some of those supercomputers, and then supercomputers like the skyscraper, right? There's always people try to be the tallest, the best, right? So there's actually a website that you can look at ranking. So luckily the US have been coming back with #1 and #2 in the last supercomputer rating. So this is Frontier at Oak Ridge, and then Aurora at Argonne. So basically we have a combination of CPU and GPU to make up really, really fast computing calculations. So those are my tools for my research, right? So here's the outline of my talk. So I'm going to try to introduce you a little bit about what the lattice-QCD is, right? I was told there would be lots of students in the audience, so I hope that's set at the right level. So if you're an expert, you want to fall into, take a quick nap, I won't find that offended at all. Then I'm going to try to get some idea how we calculate QCD observable using the supercomputer. So this is a little bit like breaking down, because people tend to have a wrong impression what lattice-QCD is, right? It's really like doing a recipe, really. We have a step-by-step process, and we try to be careful along the way and do the best calculation. And if time allow, I will try to give you some of the examples about what we are doing, and hopefully some of the things my group is doing a lot, which is pattern distribution functions. Right. So standard models, right? So the QCDs basically can be written in the cup, and that's all the standard model you need to know. Yeah, and as we know, that's very diverse, and there are lots of particles. And I'm going to use some of these references because if I get to my physics example, that might be useful. So majority, what we look at in QCD is the quarks and the gluons, right? So it's a very small fraction of that particle zoo that we're looking at, right? And so that's what the QCD is, right? And then you think it's a weird study, but and the QCD is sort of responsible for the masses we are, and then there's not a lot of study, and that's few people know about them until you are in your grad school, maybe second year, the advisor say, let's go, you should take a quantum field theory. And maybe that's when you learn about QCD. Sorry. Right. So to try to get people to be more interested about QCD, or maybe share your QCD research with your loved ones, which usually is not very interested in physics, they might be interested in games. And so it's something that actually is sort of try to let people know that the physicists actually most of the time follow simple rules, right? So you can build all these particles with some simple rules. And we start with the flavor, the quarks, and then we add on spin and so on. So we can go on to, and then we build on the heavy quarks in the degree of freedom as well. So this is actually done in collaboration with the undergrads in computer science. So here is the student who are in charge of the programming part for these others in the outreach event. And so here is my favorite photos, which is my daughter, probably 5-6 years at the time, teaching my PhD advisor how to play this game. And then there are a few things that we do in the outreach as well, right? So this is just in case the video doesn't work, right? So back to QCD, right? So we are really interested, a lot of us are studying the color force here, right? And so we have this interesting feature, interesting or complicated, depends on your definition. The strong coupling constant is a function of energy. So unlike QED, everything is straightforward, right? The QCD is complicated. So people have been studying the large scale QCD, and then you can actually derive and do a lot of pen and pencil calculation. And a lot of physics have been done, and these three gentlemen take home the Nobel Prize back in 2004 on the QCD theory. But there's still a lot to be done, and that's why it makes it really, really exciting. The low energy part of the QCD, where the coupling is strong, and they can, a lot of this approximation may not work as well And so there are a lot of room here for us to kind of explore. So I have been getting interested in this because so there are really wide range of scale that you can actually study with the QCD. At a very small scale, you can try to understand the question in terms of where the mass come from in the proton, right? How does they make up the quarks and gluon make up the mass of spin structure that we know of? And there are proton distribution function that's been universal, that's been used in many other process in neutrinos and LHC, new physics search and so on. And they can also help us understand a little bit about why we exist, right? So some of those residual strong forces kind of binding the neutron and proton together. So this is something I did in my sort of previous life. Try to study the binding energy of the light nuclei. And maybe we can live somewhere that understand why we exist, why is carbon-12 so common and so on. And maybe even in the astronomical level, right? So I first got interested in this problem because back in the time, many years ago, so people have been finding the nuclear radius to be larger than what's being expected. So there are some theory suspected that maybe the hyperon can play important roles, and that's where lattice-QCD can come in and help because hyperon is another decaying particle. It's harder to study its property, and we can maybe do the simulation and do some guidelines information there. So that's like a wide range area that one can, in principle, study if you have energy, money, and students. But to study QCD, right? So like that you learn in the class, right? We always try to write down the ground state. And then in classical physics, the ground state is nothing. So the easiest thing to describe. But in QCD, so this is a QCD vacuum. So it's supposed to be the lowest ground state. And this, what is currently plotting is topological charge distribution. So just give you a sense that the QCD background itself is dynamics and environment. So for the physics that we are interested in, this kind of degree of freedom is important. We need to take into account. So that's why I make it complicated. First you have to learn how to describe the QCD vacuum. In fact, in lattice QCD, calculating vacuum is one of the most expensive things that we have to do, right? So just take a few seconds thinking about it. Right. So it is right. So we are trying to obviously attacking the area that where the perturbation calculation isn't a good approximation, where the model isn't a good approximation. And so basically what we try to do in short, we try to take some sort of Feynman diagram interpretation of the observables, and we translate into computer code, and then we fit into computer to do the calculation. Right. So this is not new. It has been around for quite a while. So back in the late 70s, Wilson first proposed that about such a theory, which is discretize the space and time. So here is a three-dimensional interpretation of the four-dimensional space-time that we are supposed to simulate it, right? So you got quarks, like usually upward light quark, down quarks, and other degree of freedom, depends on how much quark labor you want to simulate it, right? They have quarks on the lattice side, and then gluon, instead of being treating like a field, the link information. So the gluon degree of freedom is putting on the link. And then we have something that's kind of artificial, only for lattice calculation only, something called lattice spacing, which is a bit like the resolution of your picture, right? You want that resolution to be as fine as possible. It will give you the best picture quality, right? And we want that for our computation as well. And then we often had to have a cutoff, the mass size of the system, right? So the bigger the box, the better, but that also introduce a lot of degrees of freedom, right? And so we will always want to optimize that because that translates to very expensive calculation as well, right? And at the end of the day, we want to make sure that if the quantum mass is used, it's not exactly the same as physical quantum masses. We have to do some extrapolations. And then we are hoping to do multiple lattice spacing so that we can do such extrapolation, simulate with the volume and so on. So that will be a proper way to do so, right? And if you want to look at slightly more mathematical formulations. So basically, we'll be taking observable, you will be written down, right? You have fermion, antifermion, fermion, and then the gluon fields, right? And you basically take the whole integral in space. So that's another thing that's different. Most of the time, some of you have already taken field theory classes, you're dealing with a lot of Minkowski space, which you have imaginary time. In the latest calculation, everything is real because we like to we want to do the calculation on the computer, which only take the real number. You can derive the formulation to be equivalent one or the other, just sort of a convenient choice of the space, right? All right. So this this is the setup. Okay, so why we haven't solved QCD yet? Probably like a lot of computational problems that we know of, it's a lot of time is limited by the computational resources, right? So in the 80s, that's probably many of you haven't born at the time, so you don't know what this is probably. You have this giant computer that can take up your whole desk, right? And then that's the state of the art game that you can play, some giant keyboard and so on. Today, like there's something more familiar with, you have a tiny SPS that have really, really complex graphic and vectors and so on, right? So there's a big advance in terms of computer game. That's usually how we know how great the computational resource of that decade would be like. Also how much of the science we can do, right? How actually the graphic game is really just a bunch of multiplication of matrices, right? Everything just metrics. And so there's a big part of that. Another part of that is a lot of our colleagues willing to talk to computational scientists, talking to applied mathematicians, and then really, learn about a lot of algorithm, which was discarded, totally unusable a long time ago and turned out to be useful for today's architecture, right? So that's another thing that was really, really helpful. And some of this improvement can really improve our calculation by a factor of 10 also. So things like might take 10 years to do with this additional algorithm improvement that now take 1 year, right? So that's a big significance, right? And another lesson, if you don't get anything out of this physics talk, right? What you are doing right now, if nobody appreciates it, you're probably just ahead of time. So that's why I'm thinking when I get a negative referee report anyway. Right. So it's actually happened so many times. I was one time when I wrote a paper that using a 80-20 algorithm that was considered not usable, and then turned out, hey, we can use it in our problem. So that did happen for real. So all right. So how do we do the calculation, right? So first of all, of course, you need a piece of hardware, you need computers, so you need to know where to get computed, right? So in US, a lot of lattice-QCD have been forming collaboration. So that was done before I joined. I started my research project, so that was really useful. We have a couple of people at Blue Heaven, Fermilab, and Jackson Lab, and so they each had been hosting some of the cluster. It's typically bigger than the university cluster, but not as big as the nationwide NSF-DOE computer. But that's the hardware just for lattice people only, right? So that's useful because I can do some intermediate size problem on the lattice-QCD computer, and I'm only competing with the lattice people now, like people who try to solve cancer, for example. And so we have some joint resources that we can write proposal. And the process has been getting easier. And then we can get some time on some of the latest cluster in the 3 lab. NSF have multiple, now it's SS, right? NSF have multiple computational resources across the nation that you can also, even students can write proposal, right? So you have a good idea, talk to your faculty, that you can write a proposal. They usually give you a smaller scale, just kind of trying out, make sure things are okay. And then maybe that can turn into a bigger computing proposal. So students can do this, which is something I really like about NSF resources. And then there are also DOE machine as well. I particularly like nurse machine because they like to put scientists on their computer. You can see everybody try to get except for the latest people, which are boring, but Everybody else, you can see they are definitely like some sort of local thing here. And that's like to put scientists on their computer and they alternate between male and female. And Corey is something I used a long time ago. A lot of my calculation was dating back in the day. It's no longer there anymore, but I still like this picture. And then, of course, if you are young and energetic, you can build your own. So I was really lucky when I was in Columbia. Lucky and unlucky, depends on your definition. I got to put together some of those very first powerful computer at the time. That was the younger people probably don't know. Older people, you probably know about the IBM machine. That was the pre-IBM machine that became really popular, and IBM sort of doesn't decide to do business only rather than scientific computing. So that's why young people haven't heard about that. But that was before their time, right? So I got to like, at the time it was just hanging around. I was doing a calculation that rest of the group doesn't care about. So it's like up to myself to come out with computer resources. So it's like, oh, okay, I will help out with this. So I got to put things together, combine the wire and things like that, and babysit the machine. I happen to stay nearby the university, so I can come in and out like day and night, basically, to recombine the cable to make sure it works and things like that. But not today. And then there are also a lot of software. So a lot of lattice-QCD software are available. So one of the places that you can look at is USQC website. So there's GitHub. There's actually more than one type of software, and they have a different label. There are some common lower label language we use, and then some common inverter that we can use. And then there are some very different physical, what we call physics code, which is deal with the fermion, gluon, observables, and so on. And there are multiple versions that there are a few common ones that my group use Chroma mostly, but the Neo is also very popular in US. And like where I come from, we use Columbia Physics. I forgot what the S is. Right, anyway. So there are multiple versions, and people tend to optimize. So because you can imagine, right? We don't want all the lattice people do exactly the same calculation. We want everybody will have their preferred fermions because they have specialty about making it go faster, know more about its own property. And then you want to spend your resource on something you are good at, right? For example, if you have chiral fermion, which is really expensive to calculate, and then you want to calculate observable that's really sensitive to those chiral symmetries, so you can do way better than everybody else. And for example, right? So everybody usually pay out this a little bit, right? And then there are also tutorials out there, right? So I host the latest conference. I did host the latest conference, but this is IMT summer school about the latest QCD. So this is basic QCD for physics, nuclear physics. So we have some tutorials with slides, some of the hang-on tutorials and also videos, but then IMT decided not to continue with the video services. So those videos are gone, unfortunately. But luckily, we are able to, this is from 2021 during COVID period. So we do have a chance to update some of these tutorials. And now we have a playlist. If you are interested in learning a little bit about some of the latest QCD, there's a QR code or the link if you can write it down quick enough. And so once you have that, the next thing you need to decide is what QCD vacuum you're going to use, right? Majority of the people, unless you are in really, really big collaboration, you don't really generate those QCD vacuum itself. First, you cannot publish. There's no physics result about QCD vacuum. So there's not many interesting you can write about. People usually publish one-ish paper so that people can cite to use that particular vacuum. All right, so usually it's a big collaboration effort, so you can divert out the effort so everybody have a chance to do some physics at all, yeah. Very few people with full-time jobs doing this. So there are, so this is like, so what we do is, it's a dynamic, dynamic system, right? So what we do is very similar what we do in the animation, right? Basically, it's just multiple frame that you make in the movie, right? And obviously you want that, you want to have a good resolution so that you can describe the QCD well enough, but you don't want them to be too snap. You don't want to take the snapshot too close either, right? Because it's too close. In physics, we're always worried about the data get correlated too much, right? So you're not getting individual independent measurement. So there's usually an R, you want to measure a couple of testing observable, that's easy to do, doesn't cost a lot of resources and give you some indication of those correlation. And this kind of file, this is two-dimensional snapshot of the four-dimensional matrix. In case you're wondering, they can get really, really big, right? But luckily, we are dealing with SU3 gauge theory, and there are some symmetry we can use. So people usually have certain binary file to compress it. There are multiple versions that's commonly used in our community, but then we can keep that file small, and then we can share them more easily. Right, so a lot of people will be willing to share with the latest configuration. It depends on how long it takes for them to do all the physics that they care about. Then we'll be like, who else want to use this configuration? Then you can, like everything else, download from the internet, right? So there have been some effort called International Lattice Data Grid, which is try to make downloading a little bit easier, no matter which continent you are. Oops, okay, that doesn't work. Okay. All right, sorry. Anyway, so there were a few hubs around the continents. And so that really helped downloading the make multiple copy, so you can download those a little bit faster. And then when I actually a postdoc in Jefferson Lab, we are really interested in doing something called exotic particle. So there's a really, really heavy particle, and there's an advantage of having the time duration much finer than the spatial ones, right? And those are sometimes, if your physics need a spatial, then nobody else is doing that for you. You kind of have to generate yourself, right? But this is probably one of my, probably not the top one, but top few citation involving generation of that, right? That's why some young people still kind of want to get into the game, generate their own lattices, because you got a lot of citation, right? And also do a great service for the community as well, right? Then the next thing we need to do is to calculate something called correlators, right? So we got a vacuum. Again, here's just a two-dimensional representation of four-dimensional ones, right? You create a particle on some space-time, right? So this is roughly space-time dimension, right? So if I'm interested in a nucleon, I will put 3 quarks in, hopefully in one side. I can also put them in slightly in nearby. I can calculate the quantum numbers. Then you propagate that and then analyze it in another space-time. And then we study the time dependent, which can give us some information about the energy and so on. And then if you're interested in structure or spin, masses, and so on, so you will try to put your part right before the particle and got destroyed, right? So that you can see have additional dependence of time there depends on where you put this insertion operator, you have additional time dependence that you can study the property. Right, so then the next thing we need to do is do analysis, right? So we got all these really expensive correlators. We got the vacuum, super expensive. Now we got the correlator, intermediate expensive. Now we down to something correlator that we can analyze. We can get masses if we are interested in study the particle masses, or matrix elements, right? And this is where I have been involved a lot of undergrad research to do some of this research, right? They are usually some fitting code involved and kind of get a hands-on on what's happening here. So here's just one of the posters from one of the undergrad that we had a latest conference here in 2018, which is at KLOC. So he went there and presented his work there. And then yeah, and sometimes we have to study. I'm going to skip this part. So there's something called statistic systematic, but I think I'm running a little bit low on time. But this is something that a student can get involved as well. So I have a senior and a sophomore undergrad. This is just a paper that we submitted to archive last fall, and it's currently in the referee process. So both of them are really helpful, helping us to make sure that our matrix element, ground state matrix element is dropped. It does not have big dependence on a lot of parameter choices and things like that, right? And then at the end of the day, right, if we want to say our calculation is reliable, we need to kind of carefully taking care of the monster in the lattice calculation, which can be there, right? Not all lattice calculation are good, right? So we have to think about things like systematics, especially let's say, right, we have some of this lattice spacing and finite size value effect that we need to take care of. So we often have to do repeat multiple calculation in pile masses. It is not directly calculated physical pile mass. And sometimes we do have a point or two, but because the lighter in lattice calculation, the lighter the pile mass, the noisier the data gets, so sometimes we do still do extrapolation. And then we have to study the value dependence. Usually we study something in terms of dimensionless, so n pi times L, right? Oh, and the lattice spacing, we want to extrapolate multiple lattice spacing, so you can extrapolate to 0, right? So, and only then you can have a lattice QCD prediction. So it is a long process and doing a lot of very, very careful analysis, but also a good training, I think, to become a good physicist, regardless of what you want to do afterwards, right? So there are like experiments, right? You often have more than one experiment, and then when people start to compare numbers, sometimes you do see disagreement in the lattice QCD number, right? And so that happens. And so some colleagues and myself, we kind of start with a campaign to kind of make sure that people are aware of such a system, right? There are a lot of systematic that we had to think about in the lattice calculation. That's probably irrelevant to other people doing their research method, but they just say, I want to compare with the lattice calculation. And so we create a ranking system, which is hopefully straightforward. So there are a few things in lattice people have to worry about, which is kind of labeled here. If people a good calculation, we give them a green star, right? If they not taking very carefully, like in terms of certain systematic, we give them a ray, and then something in between. How they just say good or bad, or can be further improved with a circle. So something like a kindergartner can understand star green is good, red star. And then so as you compare the latest number, that they can kind of hopefully provide a weighting, weight, right? Now, not everybody do, some people do a single, what we call simple example, which is one lattice spacing, one value, and one pile masses, compared with people who do multiple lattice spacing and do a continuous extrapolation, right? They should carry different weight between those calculations, right? But a lot of time people don't think about this multi-dimension of what we are doing, and that's where the disagreement tend to come in.
These ratings are they reached without any? I'm just curious about the sociology. Can there be contentious fights over?
Yes, that's actually a very good question. So when we first write this, nobody was putting in our own paper. That was fine. We use certain rule of thumb that's imposed by some of our heavy quark colleagues, because they have been generate very precise numbers since the early 2000s. And so the high energy community really want to take every bit of their error bar very seriously. And they have very small error, usually sometimes sub%, right? So that's a very serious number. So they have been studying some kind of rating like this for a lot of heavy quark flavor calculation. And in our case, we adopt most of them, and with some variation of in the nucleon system, slightly different from Huey-Wen system. So we take a little bit that into account, but not everybody agree. Of course, everybody will be like, they would be good to say, well, we don't think that rule of thumb is reliable. For example, that they can have certain hang arguments, come up with maybe a different assessment, right? So unless this is why it's important to do the calculation themselves, because we are talking about something I didn't go into is, so on the lattice, right, because we have lattice spacing, I can write down additional term proportional to A, right, which I can have very different fermion, very different gluon, right, action. They all lead to the same continuum, right? So and then there is also numerical technique they use, so it's hard for one calculation to say how big the systematic of the same calculation can be applicable to another one. And that's why it's important for everybody to do their own, within their own consistent method, so they can say for sure. Yeah. Yes. Oh, all right. Sorry, I thought you have a question. Right. So there are many things you can do. So I'm going to skip that. So So there are a lot of interesting one can do, and a lot of this area is not just in high energy, but also in the fundamental symmetry in nuclear physics that one can explore as well. There are electron dipole moments, some search in the diameter detections, with some, and then neutrino experiments. Sorry, I'm trying to decide what I'm supposed to talk about in my last 5 minutes. All right, so I'm going to skip this, but I hope we have, if you're interested in some of this, we can talk about this. And something I did a while ago with a colleague and with the effective theory, and I thought might be interesting because there's JD tried to do some of the electron dipole moment at F-rib with the radium, with argon with the radium generate here. And there are also, some potential beta decay, the radiated beta decay that also interesting in some of the fundamental symmetry community that can pull high energy physics. I thought it's very interesting, but I think I'm going to skip ahead and talk very briefly about parton distribution function, which my groups have been working a lot about that. Right, so parton distribution is basically it gives information, especially for nucleon, is a lot of study, and you can also get a lot of experiment to compare and then form the information, and it gives you the probability of finding a quark or gluon, that's called the parton or anti-quark, at the specific given momentum fraction compared with the Dalton photons, right? So there have been a lot of experiment going on. That's basically a lot of collision that produce proton, more or less give you some of those information, and it's all about how you reconstruct that data to give you some more of this information, right? I'm gonna skip ahead here. So yeah, so the latest have been doing things like have been doing certain calculation, but it's been doing the integral of this kind of. So for example, what we call leading twist 2 parton distribution function, which is the easiest one that you can calculate, the cleanest one on the theory. So we have been doing the integral, something called moment, right? So the example I showed you earlier, for the tensor charges, for example, right? And for experimental effort, right? So you had, so you can study unpolarized, longitudinal polarized, and transversely polarized, right? So for the latest calculation, it's very similar. You have an operator that gives you the right observable, and basically repeat all that process I just told you, and then we get the moment out of that, right? Experimentally, it's kind of hard to align the spin of the proton and then the quark spin itself, right? So generally, most of the experiments are unpolarized. You just have, two nucleon or two nuclei, proton nuclei, so on, collide, right? And then maybe you have one polarized target or polarized beam, then you can study the longitudinal polarized structure. And when you have required polarized target and polarized beam, that's when you can most clearly study the transversely polarized structure, and that's really, really hard to do experimentally. Just sort of the polarized itself, it's really difficult thing to do. Right, and so this is something that we can do, and we have one of the slides I skipped that is we can use the lattice constraint to constrain the what we call global analysis to improve the distribution here, right? But for a long time, right, we have been doing this moments, and so in principle, we have enough moment we can do an inverse problem to solve for the X dependence, right? But the difficulty comes in as we actually build the symmetry, right? So there's a price to pay. You guys probably know that from your homework, right? And so the difficulty of that is sort of we start to have very, very complicated missing that come in. That doesn't exist in continuum because you have nice rotational symmetry. We don't, right? So not all problems. One of the things, once the most misunderstanding about lattice-QCD, you can solve every single continual problem in lattice-QCD. No, right? There are limitations what we can do in lattice-QCD, right? There are certain things we do better, certain things we don't. So you do want to choose your problem carefully. The same thing with whatever method, research method you use, right? You have certain strengths, you want to explore those, right? So anyway, so there are difficulty to do so, right? And so they are very different problem that's make it really hard to do. So it's actually had to be like when I was postdoc and first get into the structure business, it had to be the holy grail that everybody know there's a problem, everybody know we can get there, and everybody is like, I've been talking to people like, how do we do that? It kind of sucks, right? We do what we can, and we only get a few moments, and we can compare with experiment because experiment don't usually have a whole range of X, right? Most of the experiment only give you a couple of X, depends on the dynamics. And so it basically is applied to all the structure out there. And so that has been a problem for a long time. And then coming 2013, I was lucky to be in a QCD workshop in Shanghai, and then Shandongji, who have been an expert in QCD and spin and structure, he proposed this very interesting idea to calculate the X dependent directly, and that's how my group got into that and at all. So I don't think I have time to go do all the details, but just want to point out that since then, in 2013, there have been a lot of different old idea and new idea that have been popping up about how to do this. So this is a very rapid field. And they are all slightly different methods, but basically they are something that we calculate, which is a lot of time image assemblement in terms of structures, to something that we wanted, which is various different X dependence, PDF or generalized Poisson distribution function, and with some perturbation calculating kernel, which is a complicated object, right? So there's certain computation that, but in principle, we do everything right, we should get the same PDF. All right, so some interesting we have been doing in our group. Okay, I think I'm running out of time. I just want to really briefly about my awesome grad student who did this calculation. And so we can also kind of ask, say what it will look like in the full time we can shrink down in a very small scale. So maybe ask me that after this, if you're still around, or some other time you can find me. Emails, and then so this is not the end of the story, right? So like a lot of method, you played around, it's good, you got a lot of first calculation out, that's great. The great feeling of being the theorist that I did this calculation first, I did this, I did that. But then at some point you hit the wall, right? There's a limitation, right? And with this particular method, we need something really, really large momentum that we can do in a moment. Right. There's a lot of this detail I can talk to you later, right? And so we have a white paper, very short white paper to try to highlight a lot of those developments and problems, right? And that's where we really need young people, very different diverse ideas that come in, can really bring in different perspective and so on, to solve some of this problem. And just very briefly, that one of the things we are trying to do a while ago with undergrad and grad students is try to kind of play around with machine learning to fill in the unknowns. And so this is one of the things I'm hoping that there's something locally at FRE, we can also discuss that. So with that, I would just leave with the conclusions. There are a lot of interesting what one can do from very precise calculations, and we make predictions, which unfortunately I skipped, sorry about that. And then we also overcome some of the problems that we couldn't do before, but we are starting to kind of play around with that. There are definitely some challenges and that require new ideas, really a new collaboration, even idea borrowed from outside our own community, which happened before. I'm sure it will happen again. And I was also a little bit about in the DOE collaboration called Exclaim, which we try to, like Dean and other people who also got awarded by the same ones, we are trying to use AI to maybe fill in some of the gaps. And then a little bit of advertisement, if you get really interesting about lattice-QCD, we have a traineeship. And unfortunately, as a theorist, they don't give us a lot of money, so we don't have a lot of spot, but we will have courses about lattice-QCD at MSU. So if it's something you are interested in, can you keep an eye out on some of those course announcements? Thank you.
Can you talk more about what Carson's doing with the machine learning?
Oh, so we are not doing anything very complicated. So this is done a few years ago, right? So we just kind of just playing around to see whether the machine. So we are doing this problem called differential amplitude, which we find is very sensitive to where we cut off. So we do matrix Solomon calculation and very sensitive how we cut off. We get very different shape. And this shape is the most interesting thing about this calculation because people have been disagreed about what the shape should look like. And so we are hoping that we can get something out of that. So what we do is we train the machine. We set some functional form and we generate pseudo data, and then we feed that to the machine, and then we test it on a complete different function form that we never did and see how well we do. And then once we train it to a state we are happy with that, then we fit our data, right? And this is where it comes in. So at the time, this is just really coming out very default function in the Python, nothing special about that. And there was some wiggling things. There are some symmetry we talk about later. There are some trick we can do. There are some symmetry we can impose we didn't do at the time. But then and a lot of my students later come and it wasn't interested in that, so we didn't expose that. And, yeah, but there are definitely a lot of things we can do with that. Yeah.
Yes, we actually have people who have thought about how to enforce some behavior of these functions and endpoints.
Right.
Yeah.
Yeah.
So this is probably just such a stupid question that it doesn't make any sense at all, but I'm curious if the gauge configurations, so you kind of have that schematic of the snapshots, is that data low rank?
Is that data what?
Low rank?
Low rank? No. I mean, like, it's pretty big actually. They are, depends on, so the lighter the pion mass, the bigger the value is, and then it can, usually need a lot of lattice site to make sure the final value is not a problem. Is that?
So if you did like an SPD on these matrices there.
It's sparse, but not low rank, right? So typically we usually have a few million degrees of freedom for the matrix that we are dealing with. Yeah, so we also like spread out the spin and colors. That's why it kind of, it is a few magnitude larger than what you think it would be. Yeah.
They look like random fluctuations, but all of the physics is in the correlations. So there's a lot of information there. Yeah.
Right. So one thing I really like about lattice-QCD is when I do a new calculation, I wasn't sure if that's right. The answer will tell me, right? If I get is this supposed to be observable, I would get something non-zero. And if I mess up the gauge transformation, I will get 0, right? And so on. So it's kind of cute too. Yeah. It's not like random number, but.
So what are the limitations of lattice-QCD in the sense that are there methods that can do certain things better, not just faster? I mean, there are certain things that there's no point to do a big computation.
Right. Right.
That are just,
so I sometimes got asked by pretty senior physicists, can lattice-QCD mathematician on the IQ?
Okay.
Which will be, yes, you can, but why would you want to waste computer that way? Right, for example, right? And so that's why we try to focus on problem over here. And so, and then another thing, like, for example, they are actually definitely more, they are real-time simulation we cannot do because we deal with a lot of Euclidean space. And so a lot of complicated dynamics structure that we can do. And things like, the reason I haven't really touched this ever since I moved here, this is to study nuclei, for example, right? It's a very computational intense, and also you are battling with the number of degree. So we try to do things from quark and gluon degree of freedom, right? And so we also run into like noise problem, which is it's not clear that we can really brute force the calculation and get something out. And that was just, for nucleon, right? So you can imagine people try to get very, very heavy quantum masses that give us a slightly better signal to noise, but nobody get beyond 6. I mean, you can play around some simple, not as you do it, but simplified case to some large number, but they are not real thing you can compare. Right, so just a few, yeah.
When you're doing structure functions, are there parts of the structure function that are much harder to get accurately, like, as you go to very, very low x's, that you run into hard problems. Or it's
Yes.
from all the way, around that.
Right.
Really spread out wrong.
Right. So they we all have that problem, but in the lattice QCD calculation, so the global, what we call global fit, which will try to combine a lot of different experimental data, and they use certain theory to be able to connect all these different experimental data and do that, right? So there are certain region they extrapolate, and there are certain region that actually fit. And so so in the latest QCD calculation, let me see which one is this probably is a good example, right? So we have so this is saying the difference between up quark and down quark differences that we calculate a lot as a function of x, right? So in the small s region and large s region, they suffer big systematic depends on how big the boosting momentum used in the calculation, right? So that's why when I personally make summary file, I will label them separately, so people don't usually kind of truncate them, right? They would just far out, look nice. But so there is some systematic that's sensitive at the low x, especially the very low x. And that's really, really hard for us to do, but we try to estimate how reliable, what's the momentum needed to calculate, say, up to EIC, for example, right? They're going to pour something to 10 to the minus, and that's 4 or 5 at least, right? Or even smaller, right? And we can really get that far. I would say the best latest calculation, a conservative estimate, you're going to hear other latest people say different things. I would say probably no more than 0.1 for now. That's the smallest as I would personally trust on the latest calculation, right? And so how do we do that? So there are, this is one of the things I skip. I don't want to have too much of everybody's time. One thing we can say, we can try to combine our latest result with the global fit, right? Global fit does have data. You can use some of the experimental data, like some of this region that we can calculate. So this is a log plot, and latest data is somewhere over the large X here, right? And if we can combine that, there's a chance that we can get some, improve some of the small s that we can calculate directly. And with the global fit, they also see a big reduction in their error because there's no data over
Is
here.
the accuracy of lattice currently the point where it actually helps narrow down the global fit, or is it
Depends on the quantity. So this is one.
anywhere?
Yeah, there is. So strange. This is a strange PDF, if anybody remembered that. And so another place that comes in, it's the here. Yeah, the polarized one. Right, the polarized structure, latest actually can do pretty well. Yeah, but not quite with the unpolarized structure because the most of unpolarized up quark down quarks, they got 60, 70 years of data, right? We only calculate this for 10 years.
You guys can compute objects that experiments can handle.
Right. Like yeah, exactly. And like our strange, for example, we can do such a calculation much cleaner because experimentally you have to do heavy nuclei, right? And you have to worry about how you treat that heavy nuclei and how all the quarks within the ions interact, and so there are other approximation there, right? Yeah. So yeah, that's what my glue is mainly focused on, trying to do, find things that's interesting that we can do better than the data, try to be complementary.
Any questions from the students?
Yeah.
Can you tell us more about the animation of the zooming in?
Oh, okay. This one. So this is something called tomography, right? So this is one of those things like when you go to CT scan, right? You want to be able to say have a nice picture of your brain structure and so on, right? This is not as complicated as that, but it's something we try to do with a proton, right? And it requires calculation of something called generalized proton distribution functions. And from there's some simple Fourier transformation. There are some, right now it was just a very simple function, like you don't have a lot of deformed it's symmetric, so it wasn't very complicated, right? So we were trying to do the same, right? We have to understand the proton more about what we can do with those, right? We try to have a better pictures of that, yeah.
And we'll ask a question on behalf of students. I think they should have this question. So you mentioned supercomputers, right?
Mm-hmm.
You mentioned students can apply.
Mm-hmm.
What are the competitors? You know?
Oh, so with the
Who
student,
they will compete
with other students. So SS, I've been trying to get my student to write a proposal, but he haven't get around to do that yet. Oops, is it being recorded? Right. So in essence, right, they actually have a spatial. If they haven't changed it lately, last time I read it, to be accurate, they do change the rule recently. So last time I read it, they have a small allocations that they put aside, and I think you are competing with other students. But I doubt it's very difficult, but I never tried that personally. But I assume because it's small allocation, just kind of demonstrate you can do some testing on that. And I think they are mostly welcome. Yeah, but I haven't did that myself. Mm-hmm.
So I heard like people doing climate simulation is a top user. At this specific.
But they were competing with other top users. So they do have like a cluster that's smaller, or the class where they have because it's small calculation, you don't usually use a lot of cores, right? So you can get a lot of off-cycle time from the cluster, right? Big user is a different issue, right? Because you have to utilize the whole system, and you have a different demonstration you need to do. You have to demonstrate your code can scale from very small to very large code, which communication turned out to be the most expensive thing you do, right? You never think about that when you use your own data, but communication is a problem for high performance computing. They're not talk to each other to take too much time when you do large scale calculation. And you can use larger nodes and you get slower result. That also happens if your code doesn't scale well.
Okay, so it's already over 5. That's sensitive speaker.
You know where to find me, and I'm in BPS, straightforward. And I have email if you want to talk to me a little bit more.